lot of glare, but whatever. So the dotted line means you added a catalyst. Whatever this reaction is, when you add a catalyst, that's what the dotted line represents. Now on a Regents, a typical question about a catalyst, short answer specifically, is they might give you something like this. Yes, sir. Sure? All right. So, can you go to the office really quick? All right, so they would give you this on a Regents, and they would say, using a dotted line, show how a catalyst changes the diagram. So what you would do is you would start at your reactants, end at your products. So you start and end at the same spot. All you would do is mimic the hump, the bump, the mountain, whatever you want to call it. Just draw the exact same thing, just shorter, right? Because it's a quicker pathway, and that's why it speeds up a reaction. So that was something I really wanted you to see and understand today. And I'm going to have you guys practice drawing those. I know it seems simple, but there's mistakes you can make. So we'll do that later. But anyways, that's the catalyst because it's shorter. All right, good. So now the question. Reactants or products, it says who has more energy?
Yeah.
So what's the answer? Products in both cases, right? They didn't give you numbers over here, right? Yeah. So we don't need numbers. This is the energy of reactants, and that's the energy of products. So it doesn't matter if you take the long way or the short way, so uncatalyzed or catalyzed, the products will still have the same energy, and so will reactants, and the products are higher than the reactants. All right, next question, please, Karen.
In terms of energy, what type of reaction is uncatalyzed forward reaction and catalyzed forward reaction?
Okay, so if you stand here at the reactants, walk up the hill, slide down to the products, Zeke, basically it's asking, is this endo or exo? Endothermic. This is endo. Whether you take the catalyzed path or the uncatalyzed, it's still gaining energy overall, right? If we assign numbers to this, 0, 10, let's say, I don't know, let's say this is 30. Our delta H, which would be here, and we're going to talk more about that today, the change in energy, heat of reaction is what that's called, would be positive 20, let's say kilojoules. So that's a positive number, meaning you gained energy throughout this process somehow, some way, probably from the surroundings. It sucked in energy, so the products have 20 kilojoules more. So that would be an endothermic reaction because the products are higher than reactants. Okay, next question. Sorry, you're going to be the reader.
What does delta H represent?
Heat of reaction. That's delta H. Okay, next.
How do the positions of the activated complexes in the catalyzed and uncatalyzed reactions differ?
All right, Nicole, what do you think? How do those positions differ? Yes, the uncatalyzed is higher, the catalyzed is lower. Again, if we were to assign numbers to this, let's say the top of this peak maybe is, I don't know, 80. The top of this peak is, I don't know, 120. Just making numbers up here. So the activated complex is where collisions occur. If they are effective, they make products. If they're not, they fall back. But the moral of the story here is less energy needed to get to the top of the catalyst, more energy needed for the uncatalyst. Okay, next.
What do these positions tell you about the activation energies of the two reactions?
All right, so I kind of answered that. Based on these numbers, Emma, could you give me an actual value, an actual number for the activation energy of the uncatalyzed?
80.
Close.
Oh, sorry, 120.
Close. Where's it start? It's not starting at 0.
Oh. Wait, which one do you want?
So I want, here, I'll help you out. I want from here to here.
110.
110. So activation energy, good job. I was kind of putting you on the spot there. That's the energy needed to start a reaction. I said yesterday that's important to remember. I'm going to say that again today. That's really important to remember that segment. So from your reactants to the top of the peak. If you don't get to the peak, you can't get over the hump. You can't make products. So that's called your activation energy. So based on these numbers I just made up, the activation energy for the uncatalyzed, that's 110 kilojoules. for the catalyzed 10 to 80, that would be 70 kilojoules. So that would be from here to here. So if you add a catalyst, it takes much less energy to get to the top. Without a catalyst, it takes a lot more. That's why the catalyst reacts faster. I'm going to show you that in like 10 minutes or 5 minutes. Next question.
How would you expect the presence of a catalyst to affect the rate of the reaction?
Okay, I'm interested to know how you guys answered this. Tell them what you think. How does this dotted line of catalyst affect the rate? Speeds up the rate. I'll take it, and no teacher's going to mark you wrong for that, but how can we say that a different way? That doesn't really answer the question, actually. Don't take that the wrong way. You're good. If you say it speeds up the rate, I'll give that to you. But what does that mean in terms of numbers? You're driving a car, and you speed up the rate of the car. What does that mean? Increase what? The speed, right? So the answer is it increases the rate. That's the answer. It increases the rate of reaction. I know to you it might be like he's saying the same thing. It's not. Increasing the speed of the, what'd you say again? Speed of the rate. It's just in science, chemistry terms, that doesn't really make any sense saying it that way. But you're fine on a Regents. I just want to tell you the right way to say it is you're increasing reaction rate, which means you're speeding it up. So I have to do my job and tell you the right way to say it. But if you write speed up the rate, you're fine. Okay? So yeah, if you take the bottom path, you're going to be able to get there faster, so you're increasing rate, speeding it up. All right? And then, is that it for that first part?
There's one more question.
At the very bottom, right?
First part.
Yeah. Okay, go ahead, last one.
Use the collision theory in combination with the information provided in the diagrams to explain the effect of a catalyst on reaction rate.
All right. Who's this going to be? Vanessa. What'd you write?
Collisions will have the catalyst used, that is, catalyst speeds up the reaction.
Okay, good. So she said more collisions will occur because a catalyst speeds up a reaction. Anybody have anything different? Okay, I'll take it. But what if I was to say, adding a catalyst doesn't actually increase the number of collisions?
So it creates a stronger, more effective.
Creates more effective collisions. What if I told you that's not true either? Because technically those are not true. So what you said, you would get credit on the Regents, but it's not completely accurate. What happens at the top of this hump right here? Reaction starts, that's where collisions are. What happens here? Same thing. The effective collisions, the number of collisions here, the effective collisions, number of collisions here, basically the same. So why does this react faster? Right, so they start colliding first, or faster. That's it. So the number of collisions here and the number of collisions here are probably the same. It's just this one, it takes less energy to get there, so those collisions start occurring faster. So again, I'm not trying to confuse you like on the other problem. I'm just trying to really explain it correctly. If you say the catalyst increases effective collisions, no teacher's gonna take points off for that. It's just technically that's not really what's going on. It just means the collisions happen first, right? Faster. Instead of here taking a lot longer to start colliding, they start colliding a little bit quicker because it takes less activation energy to get there. So that was that. All right, go to the other one. The other sheet now, please. Let me draw that. And then we'll go back and do the demo and then come back up. All right. So, can I see the picture, please? All right. So we got an exothermic reaction here. Close enough. What is this number right here? Okay. Do they even give us that? Okay. It'd be easier if I just do that for a second. All right. So they do give us this here is the activation energy, 89.5 kilojoules. They give us the delta H here, which is negative 77.2 kilojoules. And we got our reactants and our products. Okay. All right. Good. So now I'll go to the questions here. I'll have someone else help me out. Reagan, go ahead. First question.
In the forward reaction, do the reactants or the products have greater relative energy, and by what amount?
Okay, so the forward reaction for every reaction in the world means from left to right reactants to products. That's called the forward. You can actually reverse reactions and go the other way. That's called equilibrium. We're going to talk about that very soon. So if I'm standing at R and I walk to the products, that's forward. If I start at the products, work to the reactants, that's reverse. The answer to the question is reactants have more energy, but how much more? Bella, where'd you get that from? I'm not trying to be a jerk, I'm asking genuinely, where'd 64 come from?
I don't remember.
Okay, well let's start over then. You would agree that if energy is on the y-axis, the R has higher energy than P, right? That makes sense to everybody? Okay, good. So now, Bella, the number's on the board. If you're here versus here, how much higher is R than P? What number? What number separates the P and the R? Right, but the answer is 77.2. So the answer to the second part is reactants have more energy. How much more? 77.2. I know it says negative, but that's because when you find delta H, you take your products minus reactants. So it's going to be a negative number. This question is just asking what is the difference here. The reactants have 77.2 kilojoules more energy than products. Questions?
If
Yeah.
you say that the reactants did it, but can you say by delta H, or do you have to put, like, will you get credit?
Yeah,
on
delta
the-
H is fine. If you were to say that the difference is delta H, I guess, yeah, probably. Yeah. So, and don't feel bad. All right, a lot of students when they first learn this are confused with how to read this thing. So 77.2 is the difference between them. All right, next question, right?
In terms of energy, what type of reaction is the forward reaction?
Exo, why? We start out higher, end up lower. It even gives you negative delta H. This is an exothermic reaction. Next one.
What is the enthalpy of reaction delta H of the forward reaction?
Okay, so enthalpy is a word you don't need to know in Regents, but what it means is this. Enthalpy means delta H. It even said that. What is the enthalpy, comma, delta H? It literally gives it to you. The answer is negative 77.2. The delta H is negative 77.2. What is that? It's the energy this reaction loses. That's what that tells me. The reactants start with this much, products end up with this much. That's somehow, some way it lost 77.2. So that's the answer to that. Next one.
What is the enthalpy of reaction of the reverse reaction? Is the reaction endothermic or exothermic?
Okay, so eyes up here, even though they already are. If we're starting here, Kara, and we're going backwards, are we gaining energy or losing as we go from P to R this way? Forget the numbers on the board. If you're starting here and you end up here, did you gain energy or lose? Gain energy. How do you know? Good. That's all you need. The reactants are higher than the product. So if we go in reverse, so we go from P to R, that's an endothermic process. You have to gain energy to get up here. Does that make sense? Everybody with me here? Vanessa, you with me back there? All right. Sean, what is the value of delta H for the reverse?
7.2.
Very good. Positive 77.2. If to go from R to P you get rid of 77.2, then you have to gain that 77.2 to go back up to a reactant. So the answer is positive 77.2. That's actually an important concept for what we call equilibrium, which means reactions go both ways. If it's negative one way, it's positive the other, because the P and the R, they don't move. So if you go this way, it's negative, so that way must be positive. Okay, next.
What is the activation energy for the forward reaction and for the reverse reaction?
Forward, 89.5. That's really important to remember. From your reactants to the activated complex, that's the energy needed to start a reaction, called activation energy. 89.5 kilojoules. It literally gave it to you. It said activation energy. So hopefully you guys are good with that. So that's the forward. But, Amanda, it's your lucky turn here. What if you're standing here? There you go, you got really long hair. And you want to get up here. Well, first you have to get to the top. So Amanda, you have to climb this mountain and get to the top. How much energy would it take you? Because if you're here and you get to the X, it only takes this much. But this is a much bigger hill. how would you figure that out? How would we get that number?
I did this wrong, so
All right, let's just talk about it out loud. So to go from here up to here, it isn't just 89.5.
you have to add 77.2.
Very good. It would be 77.2 plus 89.5. That would get us here, because if you're given 77.2, that gets you to here. Now another 89.5. Think of meters or feet, if that helps you guys. This is 77 feet. Meters, this is 89. So you have to add them to get to the top of the hill, or mountain, or whatever. What is that number? Anyone do this? 166.7. Is the next question, which one is faster?
Yeah.
Which one's faster? So again, we got Amanda standing down here at the products, and I don't know, we'll have Zeke standing here. There's Zeke. Who's going to win?
Zeke.
So if Zeke runs and he's going to the products, and Amanda's running and she's going to the reactants, why would Zeke probably get to the products before Amanda gets to the reactants?
It's easier to go down and up.
Easier to go down than up. Okay.
I mean,
Yeah, but let's answer like on Regents. They might ask this.
Is it easier to lose energy than it is gain, I guess?
It is, and it's more stable, and there's a lot of chemistry involved with that. But let's try and simplify it. Why would it be harder? Let's say they're both racing to the top of the hill.
It requires less energy.
Yeah, it requires less. Everything you're saying, Reagan, is good. It requires less energy for Zeke to get here than Amanda to get there. So forget the whole journey. They both want to get here, and Zeke only has to go 89.5, where Amanda has to go 166.7. So does that make sense, everybody? All right. So the forward reaction would be much faster, an increased rate compared to the reverse. Okay. Is that it?
Yeah, for the first part.
Oh, next.
In second diagram, what information is given by the height of T1 curve at various energy readings?
Okay, at the height of the curve. So go ahead, flip it over. If you look at the height of T1, what does that tell us? It gives us energy on the X, and then what about the Y? The number of molecules, right. So T1 tells us not only the energy, but it also tells us the number of molecules. This is something that would never be on a Regents, but I like giving graphs sometimes and charts to read, because that's a good skill. Okay, next one, ready?
As temperature increases, what happens to the height of the curve?
All right. I gave you T1 is 100 and T2 is 400, Nicole. What happens to the height of the curve as temperature increases? Gets smaller. Starts to flatten out. And one more.
As temperature increases, how does the rate of the reaction change?
Temperature increases. How does reaction rate change? So, I guess.
The height of the curve.
Good. Next one.
As temperature increases, how does the rate of the reaction change?
Yep.
The rate of the
Sorry.
reaction also decreases.
4. Right. That's why I made a big deal about speed and increase earlier. If a reaction speeds up, that means the rate is increasing. Some kids have a hard time with that. They think for some reason that's different. The analogy of a car is the best way I can tell you. If you're going 10 miles an hour and you increase your speed to 60, so the number's bigger, you're moving faster. So if you heat something up, things react faster, that increases rate, which means speeds it up. All right, let's go back and do this demo. Somebody record this for Talia.